Continuing on with our Module 5.1 class notes, now we're actually getting down to the math of calculating and formulating equations of exponential functions. So what does an exponential function look like? What is the form of an exponential function? And how do I actually do the math of finding an equation of an exponential function? You should make the connection to compare this to something that we've done recently with, say, linear functions. That's not what we're looking at, and we're not looking at a linear function right now, but just for a moment, think back to when we were finding the equation of a linear function, and you said, I know that my linear function is y equals mx plus b, and I can plug numbers into my formula to figure out what m is, to figure out what b is, and find the equation of the line. That should sound familiar. It was on one of the benchmarks previously, so that should definitely sound familiar. We've worked that recently. Now we're doing something similar. We're finding the equation of, but this time not a line, an exponential function. Not y equals mx plus b, but the function of the form f of x equals a times b to the x power, where a represents, and you can get this straight from your pre-class notes, your textbook, a represents the initial value of the function, the y-intercept, and b is the base of the exponential. B is the number that we're multiplying by every time, either to increase that initial value if it's exponential growth, or to decrease that exponential value, or that initial value if it's exponential decay. And we'll see examples of both here. So let's consider the information we have and what we can say from this form of the function. First of all, we've got the point 0, 2000. In other words, when x is 0, y is 2000. When my input is 0, my output is 2000. One way of mathematically working through what that tells us about the function is when I input 0 for x, my output is 2000. In other words, when I replace x by 0 here, then that'll be equal to 2000, my output of 2000. But as you know, any number to the 0 power is 1. So b to the 0 is 1, and anything times 1 is itself. That simplifies quite nicely down to just a equals 2000, the initial value. The initial value at time 0, at an input of 0, my output is 2000. That's my initial value. That's my a value, 2000. Now that I know a is 2000, then I can come back to my other point that I'm given, 2, 20, that says when x is 2, when the input is 2, the output is 20. So f of 2 gives me an output of 20. So what does f of 2 look like? That looks like plugging 2 in for x in my function. I already knew that 2000 was a times b to the x is 2 equals my output is 20. So 2000 b squared equals 20. I can now solve that for b. Divide both sides by 2000, and 20 over 2000 reduces to 1 over 100. Then take the square root on both sides, and I get b equals 1 over 10. So b, my base, is 1 over 10. And then I can put this information together and say that my overall function, my formula for the function, is f of x equals a times b to the x. F of x equals a, which is 2000, times b, which is 1 over 10, to the x power. And there I've got my formula for my function. That tells me that I'm starting off with 2000 at time 0, and then every time every unit of time, I'm actually dividing that 2000 by 10. So 1 unit of time later, I'm going to divide by 10 and have 200. Another unit of time later, I'm going to divide by 10 again and have 20. Oh look, 2 units of time later, I'll be down to 20. So I'm trying to give a sense and get a sense of the connections here and see that it does make sense. It's not just a bunch of numbers that we're throwing together haphazardly. We're creating a formula that models the information that we have. And when we look at applications very soon, we will use this information to answer questions about applications. For example, this is an exponential decay formula. This is an example of exponential decay because my outputs are decreasing over time. Those questions will come soon enough, but let's look at example 10 now, where I have the same instructions, same type of problem, different numbers. Let's find the formula for an exponential function that passes through these 2 points, 3, 1 and 5, 4. The numbers are a lot smaller, a lot simpler, you might think, but they're actually not as nicely put together this time, and we'll see what that looks like as we work through the math of finding this formula, but we'll still be able to do it. Let's see what that looks like. Same thing we did last time. We say, okay, here's my first point, 3, 1. I'll plug that into my form of the function f of x equals a times b to the x. That is 3, 1 gives me a times b to the x, which is 3, equals my output is 1. So my input is 3 and my output is 1. A times b to the third equals 1. I can't do this time what I did last time. I can't simply say b to the 0 is 1 and then have my a value immediately, because I don't have a 0 power this time. That actually made things a lot easier in example 9. When we started off with a 0 power, this time I don't have that, and in fact I cannot simplify this really any further because I don't know what b is, so I don't know what b cubed is, and there's not a whole lot I can do here. Let's let this sit for a minute and come back up here and say, what about the point 5, 4? Let's plug in 5 for x and have a result of 4, an output of 4. That gives me a times b to the x, which is 5 power, equals 4 is my output. Here again, I don't know what b is, so I can't figure out what b to the 5th is, and there's not a whole lot I can do here. But what I don't like to use the word trick. The technique that we're going to use here is, now if I can't solve for a or b in the first equation because I don't know what the other variables are, and if I can't solve for a or b in the second equation because I don't know what the other variables are, then what I'm going to do is actually take these 2 equations and put them together, combine them together into a single equation. And I'm going to do so in a way that is advantageous, a way that helps me. And here's the technique that we're going to use. I'm going to combine these 2 equations by taking one and dividing by the other. That's what I'm about to show here. So let's take a look at what that looks like. I'm taking the a times b to the 5th equals 4 and dividing it by ab cubed equals 1. I'm dividing ab to the 5th by ab cubed, and I'm dividing 4 by 1. I'm literally taking those 2 equations and combining them together by dividing both sides of the second equation by that first equation. I can do this because I'm dividing both sides of the equation by the same number. ab cubed and 1 are equal to each other, so ab cubed and 1, they are equal to each other. So I'm dividing both sides by the same amount. That keeps things balanced. Now, what's the advantage of doing The advantage of doing this is now things actually simplify pretty nicely. Look at that left-hand fraction, as ugly as it is right now, and see what cancels. The A factors cancel, and most of the B factors cancel, and I'm left with B squared equals 4. 4 over 1 is 4. B to the 5th over B cubed is B squared. And I'm just left with B squared equals 4, and then I take the square root and find that B equals 2. So see there that if we combine the two equations by dividing one equation by the other, then we can cancel that factor of A and leave us with just a power of B equals a number, and then use radicals to solve for B. Now that I know B equals 2, I can plug 2 back into one or the other of the equations. Actually, it doesn't matter which one we use. You can try it in both, and you'll see you get the same answer either way. I'm going to use the first equation, AB cubed equals 1. So A times B cubed equals 1. And I'll solve for A. 2 cubed is 8. So 8A equals 1. Divide both sides by 8. And I get A equals 1/8. So now I know A equals 1/8, B equals 2. And I can go back to my function and write f of x equals A, which is 1/8, times B, which is 2, to the x power. So I'm starting off with 1/8, and then I'm multiplying by 2 every time. So I'm actually growing pretty quickly, doubling every time x increases by 1. I'm multiplying by 2 every time x increases by 1. I'm doubling every unit time. So this is definitely exponential growth. Even though I start with a small number, 1/8, I'm increasing, I'm doubling every time. So we're seeing pretty good exponential growth in this example. Again, they're not asking us to analyze that in this particular problem. They're only asking us to find the formula. We've done so, but in our next example, the last example for Module 5.1, we will see that we'll actually have to do some interpretation there.